stick and LeBron James's knees all have in common? If you didn't guess already, it's springs.
So today, our lesson is about springs, and some of you might be wondering what a spring is truly defined as. Well, a spring is a resilient device that can be pressed or pulled but returns to its original state. Springs are in our everyday lives whether you realize it or not, such as a slinky or the shocks in your car, the small spring in your pen, or even an older mattress. So, what are some things that you need to know about springs before we start? The first is K, which is known as the universal spring constant. It is different for each spring and tells you the force needed to be applied to compress or stretch the spring. This is measured in newtons per meter. The next important thing that you need to know is what X is in terms of a spring. X is equal to the amount of compression or stretch of a spring, and it is measured in meters. When talking about the amount of movement, it means how far the spring is moved away from the point of equilibrium after a force is applied on the spring. So now we know K is the spring constant and X is the displacement of the spring from the point of equilibrium. We can introduce three formulas that can be used to find different properties about a spring. The first equation is used to find the potential energy of a spring after it has been displaced. We use this equation a lot when we need to find a certain variable for energy in a system. You would plug it into the total mechanical energy of a system or just use it on its own. This equation is 1/2 K, which is the spring constant, times X, the compression, squared. An easy way to remember it is to see how similar it is to the equation used for kinetic energy. Our second equation is known as Hooke's law, and it is equal to negative K, which is the spring constant, times the change in X, or the change in displacement. This is useful because it tells us the force needed to extend or compress a spring by some distance X that is proportional to that distance. To put it plainly, Hooke's law helps us understand how a spring behaves when it is stretched or compacted. The third equation we need to know is the period of a spring during an oscillation during simple harmonic motion. This equation is 2 pi times the root of the mass over K. We will be going more into depth about the period of a spring in simple harmonic motion later in this lesson.
Okay, this has a spring in it. We can find this spring's constant if we know how high I jump in the air when I bounce on it. We know the amount it compresses when I jump on it, and we know my mass combined with the pogo stick's mass. Using conservation of energy, we can find the spring constant of this spring. So then I moved everything to the other side using division and multiplication. So you get K is equal to 64 times 10 times 0.13 times 2, all divided by 0.16 squared. When you plug that into the calculator, you get K to equal approximately 6,500 newtons per meter.
Now, you're probably wondering what the spring constant is in this everyday pen. I know it's a question that we've all been wanting the answer to for a very long time now. Well, the good thing is, we are about to show you. We're going to take this spring and perform an experiment that's going to show us the spring constant. Okay, so to find the spring constant of this everyday spring, we need to do a few things. So we're going to measure the length of this at rest using a meter stick. Then, after that, we take weight, we put it on the spring, and then we measure the spring extended. So the difference between those two things is going to give us our x, which is essential to finding the spring constant of the spring. Now all we need to do is work it out. So for this problem, we're going to use Hooke's law, which is negative k times the change in x equals mg, because that's the way that we're going to put it on. That's the only force in this problem, so that's what we're using. So negative k times the change in x, which is 0.04 minus 0.03 meters, equals 0.8, which is the mass of the bag we put on, times 10, which is gravity. So negative k, since that's what we're solving for, we get that alone on the other side by dividing out 0.01. After this, it's pretty straightforward. You just solve 0.8 times 10, gives you 8, and then you divide that by 0.01, and that gives you 800 newtons per meter. But k is still negative, so all you need to do is divide over the negative, and there you go, 800 newtons per meter, which is negative.
Terms to know for simple harmonic motion. There are 4 key terms that we need to look at when we're looking at simple harmonic motion. The first is equilibrium. Equilibrium is the state of the spring when the net force is equal to 0. The second is amplitude. Amplitude is the maximum distance that an object moves from the equilibrium position. That means if a spring is displaced in any way, whether it be compressed or stretched, then the maximum distance it moves from equilibrium is equal to the amplitude. The third term is the period. The period is the time that it takes for an oscillator to execute one complete cycle of its motion. And the fourth is frequency. Frequency is the number of oscillations an object completes per unit of time. What is simple harmonic motion? Simple harmonic motion in physics is the repetitive movement back and forth through a point of equilibrium or central position so that the maximum displacement on one side of this position is equal to the maximum displacement on the other side. What is simple harmonic motion part 2? At the maximum displacement from equilibrium when stretched, the spring is under the greatest tension. At the maximum displacement from equilibrium when pushed, the spring reaches its greatest compression. At either position of the maximum displacement, the force by the spring is the greatest and directed towards the equilibrium position. Why is it simple harmonic motion? This is just to give you a little background on why it is called simple harmonic motion. The motion is called harmonic because musical instruments make such vibrations that in turn cause corresponding sound waves in the air. Musical sounds are actually a combination of many simple harmonic waves corresponding to the many ways in which the vibrating parts of a musical instrument oscillate in sets of superimposed simple harmonic motions.
We have a spring and we have a mass. You put them together and you have oscillation. So now if we know the mass of the object and we know the spring constant of the spring, using the formula T, which is the period, equals 2 pi root m over k, we can find the period of the oscillation of this object.
So in this equation, we're finding the period of oscillation for this spring. We know the equation is T equals 2 pi root m over k, and now we plug in the numbers. So we'd have T equals 2 pi root 0.5 over 25, since that is the mass and the spring constant. That would give us T equals 2 pi root 0.02. What we would do now is we would find what the square root of 0.02 is. So we'd have T equals 2 pi times 0.14. Then we would multiply all that out, and we would get T equals 0.89 seconds. And that is our final answer.